I am Anil Kumar. Welcome to my series on polynomials. We have learned polynomial division. We understand what remainder theorem is. And in this particular video, we are going to explore the geometric and the physical significance of quotient and remainder. Here's a quick reminder of remainder theorem. When any polynomial, let's take h of x, is divided by the divisor x minus b, and the remainder is the value of the function at b, which is f of b, right? So that is the remainder. So strictly speaking, when you have a function, let us say f of x, and it's being divided by the divisor, which is, let's say, x minus b, you get a quotient here, q of x, and ultimately you may get a remainder. In that case, the function, which we have taken in our case as h of x, since the example which I am going to take is pertaining to the height of a frog with the distance, as the diagram shows here. Now, this particular division statement, which you see in the multiplication form as h of x equals to qx times x minus b plus r, can also be written as h of x divided by x minus b equals to quotient plus remainder is still to be divided by x minus b, right? So these are the two forms which we look at this equation. Now we'll understand what is the meaning of q of x and what is the meaning of the remainder r. Correct? So to understand this, let us take a real life situation. In this real life situation, we are taking position of a frog which leaps from a particular point. So let us say that our chordate plane, that becomes the origin from where the frog leaps. So we'll say that this is the x-axis and that is the y-axis. And along the y-axis, we'll give the height in units. So any unit you can take. Let's take centimeters, for example. So in that case, the frog leaps and then ultimately it follows kind of a parabolic path and lands. So this particular could be given as any polynomial equation. We'll take a quadratic equation later. But the idea here is to understand the significance of q of x and the remainder r. Now, if you look at this equation, h of x equals to q of x times x minus b equals to r, what happens when I write x equals to b? In that case, h of b will be equals to q at b times b minus b plus r. Now b minus b is 0, right? And therefore, what you get is the remainder r. It really means that if I take any instance where, let's say, the height at x equals to b, in that case, this particular height will be equal to the remainder and this height will be equal to r. That is what we're trying to say, right? So this height, which we'll say height at b, is basically the remainder r. So that is the significance of r. It's the value of the function at that particular x value. Is that clear to you? Okay. Now the second thing is, if I rearrange this, which is in the division form, h of x divided by x minus b equals to quotient plus remainder over x minus b, how do I interpret q of x? So we have understood the interpretation of r, which is actually the value of the function, correct? Now, I could also say that let's rearrange this to get what q of x is. So q of x in this case can be written as h of x over x minus b minus r over x minus b, correct? So I could write q of x as equal to x minus b is the common denominator, and we get h of x minus r. Now, does that remind you of anything? Well, it's kind of h of x is what? At any instance of time x, let us say we may again take any instance time x. Let us say we take a point x here. So in that case, the height is given by h of x, right? So that is the h of x. So h of x minus r is what? Well, it's the difference of these heights. So this is h of x minus r. Is that clear to you? And x minus b is the horizontal distance, x minus b. So what is q of x? Clearly, as you can see here, q of x is the rate of change. So q of x is rise over run. Do you see that? So that is to say, it is rate of change. It is rate of change with respect to any position x from B. From B. You get the idea, right? So between these 2 points. So that is how we could actually interpret q of x. So I hope this concept is absolutely clear, right? So let me summarize all this learning in a neat solution. So now let's look into this once again. We are looking into the geometric and the physical significance of the quotient and the remainder. So in this situation, we have taken leap of a frog as an example to illustrate. Let h of x be the height of the frog with reference to distance x from origin, right? So as I had formed this axis, so let us say that is your y-axis and this is your x-axis, correct? So x-axis and that is the height, let me say h. The function can be written as x minus b times the quotient plus the remainder. Now if x is equal to b, as you can see here, then this number is 0. B minus b is 0, and therefore we get the height at any instance as r, as shown here, right? So as you can see, so this height is r. Now r is the height of the frog at b, right? So that is the significance of r, the remainder, at any point. Now, when you look into this division statement, rearranging q of x, we get h of x over x minus b minus r over x minus b. Common denominator being x minus b. Numerator is h of x minus r, which is rise over run. Do you see this? Rise over run. And that is what the quotient is. Perfect. So quotient represents the rate of change of height. Is this clear to you? Perfect. Now let's take up the example, giving some values, right? That would be interesting. So what I've done here is that to the same question, we have just given one equation. So now, let us consider the height h of x over distance x of the frog be modeled as h of x equals to minus 5x squared plus 20x. Let us say the units are centimeters. Now you can actually answer these 4 questions. The first one is A. Find the maximum horizontal distance covered in one leap. B. What is the remainder when h of x is divided by x minus 1? C. Find the rate of change in the second second. That's a very confusing term, but I'll explain you what does it mean. Second second. And D is verify that the quotient represents the rate of change of height for the distance that begins from 1. You get the idea, right? That begins from 1. B value in this case is 1. So think about it, answer this particular question, correct? So let us look into the approach which we are going to adopt here. Clearly, h of x is given to us, and to find the maximum horizontal distance, we are looking into this position, right? So from 0 to that position. So at this maximum horizontal distance, as you know, h of x will be equal to 0, right? So when you substitute h of x as 0, you get what? You get 0 equals to minus 5x squared plus 20x, which is taking minus 5x common, you can say it is x minus 5. And clearly, that gives you 2 points which are at x equals to 0 and x equals to 5, right? So from here, it is very clear that if I take this as my origin, in that case, that is 5 centimeters. So we have this value of x in centimeters. And this is the height, h, in centimeters. So the maximum distance which is covered in one leap is 5 centimeters in this particular case. Is this clear to you? Perfect. So we get the two values where the frog is on the ground. So it leaps and then lands on the ground. We'll assume that it is a horizontal ground, right? So assumption, horizontal surface. Okay. Now, second part is, what is the remainder when h of x is divided by x minus 1? Well, the remainder, is the height of the frog at x equals to 1, correct? So now let's do this calculation over here. So first thing first, we just found what is the maximum horizontal distance. We said, well, h of x is equal to minus 5x x minus 4. Sorry, when you divide, you get 4, not 5. Let me correct that here. It is not 5, 4, right? Okay, 4. Good, we did our correction. Okay, so we get here that the distance is, which implies that 0 equals to minus 5x times x minus 4, and that gives you the value x equals to 0 or 4, and therefore the maximum distance is 4 units. The units are centimeters. So basically, this is 0 for us, and here we have 4, right? And since it is a parabola, the center will be at 2, right? Okay, so that is our height, and this is the, let's say, x. So let me just now say that this maximum will be at 2, right? So we know this point. Perfect. Okay. So we got the maximum distance, which is 4 centimeters, not 5. Now let's look into part B, which is, what is the remainder when h of x is divided by x minus 1? So we can do two ways. We know that the remainder should be the value of the function at x equals to 1. So we'll do minus 5 times 1 squared plus 20 times 1. Substitute x equals to 1, right? So that gives you what? Minus 5 plus 20. And so we get h of 1 as equal to 15 centimeters. So that is, we're saying that this height here at 1 is 15. Is that clear to you? So this is what it is. Well, why don't we verify doing the synthetic division, right? So let's do synthetic division also to verify the result. So we have the equation given to us, minus 5x squared plus 20x. The constant value is 0. And we need to divide by 1, right? Okay. So let's do the synthetic division. So bringing minus 5, multiplying by 1 gives us minus 5, adding gives us 15, and then multiplying, get 15, and adding, we get 15 as the remainder. Perfect. So as you can see here, that the remainder is 15. So the calculation is absolutely correct. You get the idea? But from here, we can also write the height in the factored form, in the quotient form, which is quotient is equal to minus 5x plus 15, correct? And then we have a remainder, which is plus 15. So plus 15 over, we need to divide this by x minus 1. Okay? So that becomes our division statement. Is this clear to you? So from here, we do get the quotient. So we can say that the quotient in this particular case is minus 5x plus 15. And remainder is equal to 15. Clear? Perfect. That will help us actually to solve part C and D also, right? So remember this. Okay. Now let's talk about rate of change. So now part C is to find the rate of change in the second second. Now what does that mean? See, this is like first second, right? And that is the second second. Do you see it? Second second? This is 0, that is 1, this is 2. And we know it landed after 4 centimeters. I should say second centimeter in this case, because we have taken length, not time. So second centimeter. Okay. The function is with respect to the... So first centimeter is this unit, correct? 0 to 1. Second is from 1 to 2. When the leap is between the distance of from 1 to 2. That is the second second centimeter. Okay, right. How can we do it? We need to find rate of change, right? There are a couple of ways to do it. One is we can find this rate of change by using a formula, that is the position at the second centimeter minus 1 over 2 minus 1, correct? So that becomes the rate of change. So if I plug in 2 here, what do we get? So if I plug in 2, let's calculate, right? So what is h of 2 equals to? H of 2 will be minus 5 times 2 square minus plus 20 times 2, which is basically minus 4 times 4 is 20 plus 40. So it is equal to 20, correct? So we could write this value of h2 here, which is 40. And h1, we found this was 15 earlier, and 2 minus 1 is 1. And therefore, we do get, 20, not 40, we get 20, right? So 20 minus 15, and that gives us rate of change of 5. So what we're trying to say here is that these heights, and that is the slope, right? So that is the rate of change we're talking about. So we found that this height, when the distance is 1 centimeters, is 15, right? So this is 15 for us. And that one is 20 for us, correct? So this will be how much? That will be 20 minus 15, which is equal to 5. Is that clear to you? And this unit being 1, rate of change is the slope. You get the idea. So that is how we could find the rate of change. Perfect. So once again, to find the rate of change, what do we need to do? We need to find what is the height at 1, right? Which is h of 1. We know h of 1 is 5 for us. We just calculated earlier. Then we calculated h of 2, which is 20 for us, right? And then we 15 was h of 1. And h of 2 is 20 for us. And the rate of change is given by the formula h2 minus h1 divided by t2 minus t1, or x2 minus x1. So that is one thing. Now we also learned earlier that quotient gives you the rate of change, right? So the quotient which we found was what? Let's check this out. So earlier we calculated the quotient from synthetic division. Minus 5x plus 15 was the quotient, right? Minus 5x plus 15 was the quotient. Now since we want to find rate of change in the second centimeter, so from 1 to 2, we could find what is the value at 2. So if I substitute 2 here, what do I get? Let us calculate. We get minus 10 plus 15, which is also 5. Do you see that? So that is the rate of change. The unit will be centimeter per centimeter. Now you should not be cancelling this unit, because one unit is telling you rise which is the height, and the other one is the run, which is the distance, correct? So if this is height over distance, 5 centimeters per centimeter becomes the rate of change. And you can see here that the rate of change, let me write, rate of change is equal to the quotient for 2, right? With respect to the first position was 1, we divided by x minus 1. So from that position, you get the idea. So that is how we can connect the two things. I hope this concept is absolutely clear. Now let me summarize our learnings for this particular case. We basically took this example just to verify the significance of qx and the remainder r. R is the value, right, at any point. So if this point is, let us say, in our case 1 in the frog example, then this height will be equals to h of 1, correct? And at 2 centimeters, the height will be h of 2, correct? So the rate of change will be what? Will be h of 2 minus h of 1 over 2 minus 1, correct? Which we got as 5 here, right? Because this was 15, that whole distance was 20, right? And this will be 20 minus 15, which is 5. And then 2 minus 1 is 1 unit, correct? And therefore, this slope is basically rate of change, which is 5. We also calculated that the quotient q at any point when we divide by x minus 1 was what? Was basically minus 5x plus 15. Since we wanted rate of change at 2 from 1, this is what we're looking at, correct? So we can find what is q of 2. Substituting 2 here, we get the same result, which is 5. Is this absolutely clear to you? So with this example, I think it should be absolutely clear that the remainder will give the value of the function at that particular point, and q of x will give you the rate of change with respect to the point b, right? Between b to x, right? So basically, if it was 1, then it is from 1 to 2, but if it is b, then the rate of change will be from b to x. So remember here, if this point is b, and let us say this point somewhere here is x, then the rate of change q of x is this slope. Is that clear to you, right? So that is q of x. Perfect. And the remainder r is this value. Value the function at these points. So here the remainder will be, here it will be h of x, here it will be h of b, right? So that is the summary. So now I hope you understand how they are very much related with the slope and the value of the function at a given point. Feel free to write a comment, share your views, and in case you want to learn from me, you can attend my classes. For that, you may send me an email on the address given here, and then we can work it out. I hope you find it interesting. Thank you, and all the best.